Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called high power autonomous optimization software for electric sector enterprises. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence.
High-power mathematical modeling framework is based on the concepts of
artificial hypothalamus,
that is the formal and strong integration of artificial intelligence and mathematical programming. The hypothalamus of a multi-business energy enterprise is the result of the integration of mathematical models of predictive analytics and prescriptive analytics of several subsystems. Hydro system, electricity system, natural gas systems, and smart grid systems. Presence. High-power optimization decision support system oriented to support decisions in electricity systems, electricity wholesale markets and smart grids. According to the structure of modern electricity markets, the support of the business decision-making power generation should be seen from several points of view. Central agents, formed by the regulator, supervisor, planner, and system operator. Generators, agents that operate power plants. Distributors, utilities enterprises. Traders. Smart grids operators, and industrial companies. High-L, high-SGO and high-gas together and make high power that is set simulation models optimal dispatch of electricity and gas systems. High-L, electricity supply chain optimization, models designed to support the decisions of the various actors involved in the electricity supply chain. High-SGO, smart grids optimization, models designed to support the decisions of the various agents involved in the smart grids business. High-Gas, natural gas supply chain optimization, models designed to support the decisions of the agents involved in the natural gas supply chain. High-L and high-SGO cover all levels of the electricity systems. Electricity system and wholesale market optimization models. Physical modeling, hydro system. High water corresponds to a general model that includes all kinds of hydraulic components, reservoirs, hydroelectric power plants, pumping stations, pumping storage, rivers, overflow channels, connection points, demands, irrigation, aqueducts, environmental, industrial. Components can be freely linked to form any topology. Hydroelectric power plants are modeled independently of reservoirs, so plant reservoir and reservoir plant connectivity must be established. The regulation capacity of the reservoir is simulated in detail, so such a simulation consistently represents the dispatch of the power plants, considering their ability to regulate the multi-annual, annual, hourly water resource. For special reservoirs, it is possible to generate established operating rules based on agreements or laws that must be observed when using water resources. Physical modeling, electric system. Electrical connectivity is carried out through a network of circuits, links, and bars, nodes, that integrates different types of installations, power plants, hydroelectric, thermoelectric, coal, wind, solar, biomass, places of demand, industrial, cities, regional interconnections and energy storage. For each type of electrical infrastructure, high power includes the exact equations for simulation. High power includes the simulation and several types of renewable energy sources and energy storages. Physical modeling, natural gas system. High gas describes the process of supply and demand of natural gas. From this point of view, its integration with the electricity system determines the economic balance electricity-gas. The entities of the natural gas system are node, connect the gas system installations. Production fields. Consumption zones, discriminated by sector, example, refineries, heavy industries, residential, vehicular, and commercial. Thermoelectric power plants. Transport systems, pipelines and multimodal transport systems using vehicles. Pumping stations, compress the gas to transport it, and ports, receive and or ship liquefied natural gas, LNG. They are associated with liquefaction and or regasification plants and have gas storage capacity. Connectivity between the electricity and gas sectors occurs through the demand for natural gas for use in thermal plants, and the substitution of the demand that can occur between gas and electricity. High-L mathematical models make up a flexible decision support system that provides different types of services in an integral way. They can be classified into integrated dispatch of generation plants, optimization of generating agents, and predictive analytics of stochastic processes. Traditionally, the optimization models in the electricity sector have been individual modeling with exogenous coordination between models, based on multi-stage stochastic programming, and using large-scale optimization methodologies. The differences provided by high power are integrated holistic modeling, scientific risk modeling, multidimensional uncertainty, parallel optimization, and autonomous real-time distributed optimization. The EED, Electricity Economic Dispatch, model optimizes the dispatch of generation infrastructure, minimizing the cost of operating the electricity system, which simulates a perfect electricity market. EED is the core model of high power, as its equations/constraints are used in multiple specific models that the agent requires to address decision support needs. From EDD, 3 models of complementary dispatch are built: Economic Perfect Dispatch, Economic Regulated Dispatch, Nash-Carnot Equilibrium Dispatch, and Unit Commitment. The first 3 models are oriented to planning and the fourth to real-time programming. 3 types of connectivity of the generation system and the transmission power grid are considered: ideal single node, ideal dispatch ignoring the transmission system, electric transmission network connectivity based on the detailed connectivity of the electricity transmission system using bars and circuits, operative areas connectivity, when the user does not have, or does not want to use, the detailed configuration of the electricity transmission grid. It is possible use the connectivity based on operational area //app, Blaster Online, com/speech low/changelogs including limits on the transfers between areas. Interconnection electricity, gas integrates electricity network with natural gas network. Interconnection electricity, water can be fully detailed, including travel times between nodes and transport restrictions in water resource conduction channels. Economic regulated dispatch, delivery of plants that minimizes the cost of operation of the interconnected system and includes representatives aspects of the regulatory of the electricity market being simulated. It does not correspond to a model of economic equilibrium, however, it is an easy and fast way to represent regulatory considerations based on optimization models. Carnot-Nash equilibrium, dispatch of plants oriented to the simulation of competitive electricity markets with agents that can influence their decisions on transactions occurring in the market. It can be used to, among others, project the dispatch of a competitive market, and study the exercise of dominant power of agents.
The diagram presents the design of the integrated use of mathematical models to support the decision-making of a generating agent.
4 models are considered fundamental to support the strategic, tactical and operational decisions of the agent. Electricity dispatch and financial analysis. Integration dispatch models with ALM, assets liabilities management, financial models, including risk management, to perform analysis of the financial impact of decisions. The main applications of high-power ALM are the valuation of income and expenses of investment projects, energy installations, and valuation of companies. Integrated optimization of investments by global energy companies, taking as a reference the regulatory laws of the different regions or countries. The financial modeling results individualize the operating income and expenses, and can include all types of legal accounts. Electricity supply chain design and risk management, associated with strategic planning, long-term decisions related to design supply chain, in relation to capacity of reservoir, transfers, power plants and other assets of an electrical system. It includes risk management and financial planning. Energy trading and risk management. Optimal decisions related to trade energy and coverage of financial risks based on standardized or bilateral contracts. It corresponds to a set of mathematical models aimed at supporting the decisions of the different agents involved in energy trading in I. Long-term market, 2. Spot market, and 3. Secondary markets. The result of a risk analysis is the definition of Pareto curves of financial risk versus expected revenues/costs, based on which the decision maker must define the risk position he wishes to assume, varying between risk-prone and risk-averse. Maintenance optimization is oriented policy making preventive maintenance of multiple central generation plants and others electrical assets. It can be applied to all assets in a regional or national grid. High Power Man can be implemented following the principles of PHM, Prognostics Health Management, for industrial asset maintenance, integrating specific models of predictive analytics for asset components and prescriptive analytics to optimize the integrated operation of the asset network. High Power has been used by ISO, in Peru, and market supervisors, in Colombia, for planning and decision-making purposes. High Power includes some predictive analytics models. Spot price modeling in a free market. The prediction of spot prices of the energy market is fundamental for the decisions made by an agent that participates in that market, whether buyer or seller, generator, trader, or distributor of energy. This is because the decision maker requires that models that produce spot prices be used in other mathematical models within the decision-making process. The mathematical models to be used depend on the planning period, real-time/short/medium/long-term, and the type of market considering the dispatch of the plants, by mathematical model, or by offers of market agents, free market. In the case of a free market, the situation is complex since the law of price formation cannot always be explained based on mathematical rules, explicit, clear and universal, that already integrates a mathematical model of dispatch. Synthetic generation renewable energy sources. For the generation of synthetic scenarios of climate variables, there are two requirements: short-term, hours, days, and medium/long-term, weeks, months. Specific short-term models must be built for each renewable source. For the medium and long-term, there are three alternatives to generate synthetic scenarios. Synthetic statistical model for the generation of climatic variables, firing Metallis type. Generate synthetic series of climatic variables based on the mixture of historical series. Generate synthetic series based on the historical series having the ENSO series, El Niño Southern Oscillation, as an instrumental variable. Projected short-term hydrological contributions using variations and enhancements of Kalman filter. All Power L models share the same data model, input and output, in such a way that communication between models is direct. In the same way, all models make up the artificial hypothalamus of the wholesale market of the electricity sector.
Smart grids optimization models.
In a regulated environment, generation, transmission, and distribution are operated by a vertically integrated enterprise, usually a state-owned enterprise, which has a monopoly on the supply of electricity. Conversely, in a deregulated environment, different parts of the electricity grid are owned and operated by different actors, and electricity markets provide a platform that fosters competition among participants. As each smart grid is particular, it requires a specific decision support system that allows the operator to interact with the entire electrical system. HiSGO provides all the analytical elements necessary to configure the specific DSS that each case requires. HiSGO is composed of forecasting models and optimization models aimed at supporting the decision-making of electric agents, smart grids, optimization of the economic and technical aspects related to smart grids and electricity companies. Demand response for buildings and/or housing, demand response, optimization of energy management in facilities, such as universities, shopping centers, office buildings, homes, urbanizations, and small towns. Industrial energy efficiency, optimization of energy management in heavy industries intensive in energy consumption. Forecast renewable energy sources. They correspond to predictive analytics models focused on the prediction in the specific sites where are located the generation plants. Forecast of demand energy. Long run. Demand projections per weeks, energy and maximum power. Medium term. Demand projections per weeks, located in medium areas. Short term. Demand projections per days or hours, located in specific installations. Real time. Demand projections per fractions of hours, located in specific installations.
HiSGO is integrated by the following optimization models: economic/regulated dispatch of the smart grid, optimization of the management of electrical energy in small cities, factories, universities, shopping centers, office buildings, urbanizations. Smart grid unit commitment, optimization of the short-term optimization of the electrical load in real time. Smart grid configuration, optimizing the network topology. It considers voltage control, configuration of feeders, location/activation of electrical assets, transformers, capacitors, and phase balancing. Smart grid design, optimization of the design and/or redesign of smart grids with modern power technologies. ETRM, electricity trading and risk management, decisions to buy and/or sell electricity, in a long-medium short-term market, one day in advance and the day of dispatch.
Industrial energy efficiency. The technical economic viability of energy storage coupled with the proliferation of energy technologies based on renewable energy sources has changed the landscape of the industrial sector, since it is now possible, and increasingly efficient, to generate renewable energy and store it for use in due time. This implies the tendency to standardize the marginal costs of generation around an average value for all periods and all the nodes of the electricity grid, capturing the benefits that this entails. In practice, all industrial companies can be agents that interact in the electricity market, since it is possible for all to act as co-generators and carry out commercial activities and transactions. This, together with the Industrial Internet of Things, increases the pathways to achieve industrial energy efficiency. Industrial energy efficiency results of the integration of production processes, transformation of matter, with industrial energy services, energy transformation, aimed at the simultaneous optimization of both industrial production and energy conversion that is related to polluting emissions of gases and liquids, associated with increasingly demanding environmental control laws. The high-power and high-SGO models can be integrated with complex industrial process models, in which it is necessary to redesign the power supply system according to the new power technologies. This type of model includes the simulation of polluting processes, for example, combustion in furnaces, to determine the optimal mixture of fuels in accordance with environmental regulations. High power and high SGO integrate the models and information systems around a common data model, allowing models to be connected automatically through the database or through RAM memory, integrating them as an artificial hypothalamus for an electricity company of wide coverage.
Optimization under uncertainty and risk management.
Optimization under uncertainty is integrated by: first, robust optimization when the parameters of the model are characterized based on variation ranges, and the objective of the model is to produce the best solution considering the worst situation for the occurrence of the parameters. Second, stochastic optimization when model parameters are characterized probabilistically and therefore all results can be associated with empirical probability distribution functions that depend on the risk management policy. The stochastic optimization process. It is composed of 3 stages: identification of the stochastic process model, implementation of a synthetic scenario generator, and design and implementation optimization stochastic model for decision support. Stochastic optimization implies the definition of the decision-making process, definition of the uncertainty dimensions and the stochastic processes associated with parameters, the risk management policy, and the approach to use for the computational solution. There are multiple decision criteria, objective functions, that can be integrated into models which are associated with the risk management policy and risk position, prone or adverse, of the decision maker. Scientific, financial and operational risk management is the true benefit provided by stochastic optimization models. The complexity of this problem lies in its bi-criterion nature: maximizing the expected revenue and minimizing the risk assumed in decisions under uncertainty. This is summarized in the Pareto curve: risk versus expected revenue, which is the final information produced by mathematical models to support decision-making. Since the end of the past century, the mathematical formulations to control the CAIR and mathematical programming models were developed. Rockefeller and Yuri Yasev, 2002, Conditional Value at Risk for General Loss Distributions. These methodologies, for the scientific financial risk management, have been included in high-power models to control/manage financial risks and operational risks. The third foundation of mathematical modeling in high power is large-scale optimization methodologies. In the future, the real-life problem solution based on mathematical programming, applied to large physical and social structures/organizations, must be based on multi-level parallelism using the modern computational architectures. Then, large-scale optimization methodologies are the way to atomize an optimization mathematical problem in multiple types of subproblems that can be solved using the concepts of asynchronous parallel optimization and real-time distributed optimization. High power may use methodologies like Bender's theory, Lagrangian relaxation, Dantzig-Wolff decomposition, column generation, disjunctive programming and its variations. These methodologies may be combined using cross-decomposition concepts to implement parallel and/or distributed optimization. To speed up the solution time of large-scale problems, Hy created the algorithm GDDP, Generalized Dual Dynamic Programming. GDDP is oriented to solve dynamic optimization problems, integrating the Bender's theory and dynamic programming approaches. Based on the dynamic programming approach, GDDP makes a distinction between state variables and control variables. This distinction permits a more detailed algorithm in which the subproblems are smaller than in the algorithm's nested Bender's decomposition, NBD, widely used in the economic dispatch of power systems. The main limitation of NB, including dual dynamic programming, DDP, is that they only solve linear models, then GDDP is more robust than NBD. As you see in the table. The table presents a benchmark, realized by Hy, between standard GSDDP and standard SNBD, stochastic nested Bender's decomposition, like SDDP, using a stochastic linear economic electricity dispatch. The experiments show that the low complexity of the case does not always justify the large-scale methodologies. The best GSDDP option is, approximately, 100 times faster than SNBD, and the best GSDDP with NBD coordinator is, approximately, 15 times faster than SNBD. The following table and image resume the study of behavior of GSDDP for a stochastic mixed linear economic electricity dispatch. The decrease in the solution time per scenario, when increase the number of scenarios, is a measure of the learning capacity of the GSDDP.
The new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers, will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Thank you very much for your attention.